Welcome back. So let's take a look at what's happening uh, atomistically as we stretch a crystalline material. So for the rest of this particular lecture, we're going to be talking about crystalline materials. We'll talk about elasticity of rubbers and viscoelasticity in the next week. I'm going to rearrange the course a little bit. Previous years I taught that after plasticity of crystals, and I think I'm going to go back and change the order. Okay, so let's think either a ionic solid or a metal here. And if you remember your solid state physics or ceramics course, we know that we need two criteria to make a stable bond, right? That the atoms should be attracted to each other the closer that they get. So there needs to be an attractive energy, but there also needs to be a repulsive energy, right, to keep the atoms from smashing into each other and fusing. So there's a repulsive energy that's stronger but decays faster than the attractive energy does. And the summation of these two energies gives you an energy minima, right, at your equilibrium. This is the bond energy, right, at your equilibrium distance. All right, for ionic solids, right, we have a energy relationships that look like this. For metals, we typically do a Leonard-Jones or some other similar type potential. But the main idea is that your repulsive energy needs to decay faster than your attractive energy. Now we also know that the derivative of energy with respect to this distance is going to be our force. So where the force curve equals 0, right, that's our equilibrium bond distance. And then what we're going to do is zoom in. And we're going to consider very small perturbations around this equilibrium position. And if we zoom in far enough, right, even though this is a curve, if you zoom in on any curve far enough, right, you basically have a straight line. So this is our elastic response of a crystal, right? We're doing small perturbations about our equilibrium atomic positions. And if we think back to our undergrad stress-strain test, right, we start and we load up and we come back down, right, and we're back. We follow the same path down. We have this linear elastic region in our material. So in 1D, we would say that the stress is equal to the Young's modulus times force, right, or stress over strain. The slope of our stress-strain curve is our Young's modulus. In 3D, we're going to generalize that to a tensorial form. So we're going to say stress is equal to a elastic stiffness tensor times our strain tensor. All right, so in indicial notation, we have sigma ij is C ij KL epsilon KL. And right, notice the analogous form to a matrix vector product, right? So you know in B, I equals A I J C J, right? The last term. So here we have the last two terms. We're doing a contraction of the last two terms of stress, of our stiffness with strain, to give us the stress. And we can invert that, and we can say our strain is equal to our elastic compliance tensor times our stress. Now don't ask me why C is stiffness and S is compliance. Just remember that's the way it is. Okay. So crystals belong to this class of what we're going to call hyperelastic materials, right? That's where our stress-strain behavior can all be defined in terms of a strain-energy density function. And in terms of small displacements, we say that the derivative of our strain energy with respect to our strain is our stress, Cauchy stress. For finite deformations, we can write our strain energy with respect to our first Piola-Kirchhoff stress or a second Piola-Kirchhoff stress. And here's how our Cauchy stress, it's kind of nasty. So this is what we call work conjugate stress strain measures, so that it gives us the relationship to our strain energy, or our work conjugate. Stress strain measures gives us our rate of work. So our first Piola-Kirchhoff stress and our deformation gradient are work conjugate stress strain. Our second Piola-Kirchhoff stress and our finite Green-Lagrange strain are work conjugate. And Cauchy stress isn't work conjugate to anything useful. You'll also maybe see a term hypoelastic stress, or hypoelastic materials, and these are distinctly different. Right, the hypoelastic materials, you have some stress that is some stress rate is related to a work rate, and we're not going to go into, or a deformation rate. I'm sorry, I did not want to say work rate. Hypoelastic is our stress rate is related to our deformation rate, and we won't talk about those. But I just wanted you to make sure that if you saw the term hypoelastic versus hyperelastic, you didn't get them screwed up. Hyperelastic is we are relating our stress and strain through our strain energy density. Okay. Again, I want you to think about something, and it's not at all hard to show that from the definitions of our elastic stiffness tensor and the way we went through it, to show that our strain energy density is 1/2 sigma ij epsilon ij, or the double contraction, the double dot product of our stress and strain tensor divided by 2. And to show that linear elastic materials are hyperelastic. It's pretty straightforward. I want you to play with it. If you have any questions, ask me in class. Okay, so let's look at some of the properties of our stiffness and compliance tensors. Well, first, they're inversely related to each other. Right? So what does it mean for the fourth order tensor to invert a fourth order tensor? Right? So basically, if I were to multiply these, I would get the identity tensor, fourth order identity, but it goes a little beyond that, right? It's that if I multiply S, right, multiply by S, right, I would get S sigma equals SC, which is C inverse times C, so identity epsilon. So it's a way of moving back and forth between these two equations. Even though it's a fourth order tensor, it works exactly the same. So a generic fourth order tensor, right? We have 3 to the 4th components, I, J, K, and L. So that gives us 81 terms, right, for an arbitrary stiffness and compliance tensor. But we have symmetries that can reduce these number of terms, right? We know that stress is symmetric. Sigma ij equals sigma ji. So Cijkl has to equal Cjikl. That brings us down to 54. We know that the strain is also symmetric. So Cijkl equals Cijlk. That brings us down to 36. And since we know that the derivatives here of our strain energy density with respect to strain, right, the order in which we do these partial derivatives doesn't matter. Right, so that brings us down to, gives us the symmetry that Cijkl equals Cklij. So that means we have 21 components, independent components of our elastic stiffness and compliance tensors. So that means if we had a arbitrary material with no crystal symmetry whatsoever, we would need 21 terms to describe our elasticity, right? But of course, material symmetry is going to reduce this greatly through the application of Neumann's principle, right? So many of the terms will show that they have to be either 0 or equal to each other. Okay, we're going to, the next part of the lecture is going to be on isotropic elasticity, and then matrix representations of elasticity, and then we'll come back to anisotropy and discuss what the forms of the stiffness and compliance tensor have to look like for common crystal systems. Okay, thanks for listening.